Section 5.3, present value of annuity and amortization. Suppose that at the end of each year for the next 10 years, $500 is deposited in a savings account paying 7% interest compounded annually. This is an example from the last section, which we called ordinary annuity. The present value of an annuity is the amount that we would have to be deposited in one lump sum today using the same compounded interest rate in order to produce exactly the same balance at the end of 10 years. So instead of putting in quarterly or monthly, etc., what would we need to put in for one lump sum in order to produce the same amount we would have had we made payments? So our formula is listed as below. So R is the payment that we're making. Again, R is the rate. M is how often compounded, so how often compounded. And then T is how many years. So the variables are still all the same since the beginning of Chapter 5. Also note that we are bringing our power as a negative power, so keep that in mind as we simplify. Tim and Carol are both graduates of the Brisbane Institute of Technology, so BIT. They both agreed to contribute to the endowment fund of BIT. Tim says that he'll give $500 at the end of each year for 9 years. However, Carol prefers to give one lump sum today instead of making payments. What lump sum would she need to give that would equal the present value of Tim's annual gifts? If the endowment fund is at 7.5% compounded annually. So we need to find out how much that she has to give today in order to equal the same amount that Tim is contributing. So Tim is currently contributing $500. And using our formula from above, we're going to have 1 minus 1 plus. Our interest rate is 7.5%, so 0.075, divided by compounded annually, so 1, to the power of negative 1 times 9 years, all over 0.075 divided by 1. So 500, 1 minus 0.075 divided by 1 is still 0.075. And if we add 1 to that, so 1.075 to the power of negative 9, all over 0.075. Again, we're dividing by 1. So simplifying a little bit here, we'll have 500 times 1 minus 1.075 to the power of negative 9 is 0.052158 rounded, divided by 0.075. So if we were to subtract our numerators, divide by 0.075, and then multiply that quantity by 500, we will see that Carol will have to give right now $3,189.44 in order to match if Tim were to give $500 annually, so that they would be able to give the same amount. What I'd like you to do is pause the video at this time, and I want you to try to find the present value of an annuity of $120 at the end of each month, put into an account yielding 4.8% compounded monthly for 5 years. So I want to know how much I would have to put into this account right now today instead of giving $120 at the end of each month. When you're done, go ahead and press play and we'll do this together. So we are currently putting into the account $120 using our formula of 1 minus 1 plus, our interest rate is 0.048, and we're compounding monthly, so divided by 12 to the power of negative 12 times 5, all over 0.048 divided by 12. So this is equal to 120 times the quantity. 0.048 divided by 12 is 0.004. And if we add 1 to that, we'll have 1.004 to the power of negative 60, all over 0.004. So 120 times the quantity. If we take 1.004 to the power of negative 60, we'll have 1 minus 0.787 divided by 0.004. So using our calculator, again, that's rounded. We'll take 1 minus 0.787, divide that by 0.004, use that quantity to multiply by 120, and we will see that we will need to give $6,390 today in order to match if someone were to be giving $120 per month. A car costs $19,000. After a down payment of $2,000, the balance will be paid off in 36 equal monthly payments. So if we have 36 equal monthly payments, do we agree that that is 3 years? With an interest of 6% per year on the unpaid balance, find the amount of each payment. So, if we had $19,000 and we give them $2,000, we only need to reach $17,000. That's what we need to reach. And we don't know what our payment is. Okay? But we can use the rest of the formula. So 1 minus 1 plus our interest rate is 0.06. We're paying monthly times negative 12 to 3 years. All over 0.06 divided by 12. So $17,000 equals our rate, 1 minus 0.06 divided by 12 is 0.005, so 1.005 to the negative 36th power, all over 0.005. So 17,000 equals 1 minus 1.005 to the negative 36th power is 0.83564 over 0.005. So if we were to use our calculator and take 1 minus 0.83564 and then divide that by 0.005, we would end up with 17,000 equals R times 32.872. Now in order to get R by itself, we want to divide. So $17,000 divided by 32.872, we would have to make $517.16 per car payment. So let's use the same information from the previous example here. And instead of having 36 equal payments, we're going to have 48 equal payments, which is 4 years. And our interest rate is slightly less. Let's see how much our car payment would have to be then. So we have $17,000 still that we're paying. Again, we don't know what our payment is. Take 1 minus 1 plus our new interest rate, so 0.054 divided by, again, we're still making monthly payments, to negative 12 times 4 years, all over 0.054 divided by 12. So let's start simplifying using the order of operations. All right, so 0.054 divided by 12 is 0.005, so if we add 1 to that. Negative 12 times 4 is negative 48, all over 0.0045. So $17,000 equals our payment times 1 minus, well, if we were to take 1.0045 to the negative 48th power, we would end up with 0.806126 over 0.0045. So subtracting and dividing, we'll have $17,000 equals our payment times 43.0831. So to get R by itself, we'll need to divide by 43.0831. So our payment would have to be $394.54. A loan is amortized if both the principal and interest are paid by a sequence of equal periodic payments. So again, we have a formula that will tell us how much our payments need to be so that they're equal amongst the whole time. Again, the formula above, P represents how much we're borrowing, so the principal. I'm not going to go through R and M and T again. R is the rate, the little r is the rate, M is how often it's compounded, and then T is for how many years. So the Perez family buys a house for $275,000 with a down payment of $55,000. So they're only mortgaging $220,000. They take out a 30-year mortgage and an interest rate of 6%. Find the amount of the monthly payment needed to amortize this loan so that they have equal payments, but yet their payments cover both the principal and the interest. So we're borrowing $22,000. We're going to take this by our rate, 0.06. We're paying monthly, so divided by 12. All over 1 minus 1 plus our rate over how often we're borrowing to the negative 12th times 30 years. So this is equal to $220,000. 0.06 divided by 12 is 0.005. All over 1 minus 1.005 to the negative 360th powers, because they're making 360 payments. So if we multiply our top, we'll end up with 1,100. And if we take 1.005 to the negative 360th power, we'll end up with 0.1660. Subtracting, we'll get 0.834 rounded, of course. So our payment would have to be $1,318.94. That would be our principal and mortgage payment. Using this information, let's determine how much of the loan was actually the amount of interest. Well, if we have our payment is $1,318.94, and we multiply that by 360 months or 360 payments, that means over the lifetime of the loan, we will be paying $474,820.14. But the original loan was only $220,000. So if we subtract these, we subtract how much we paid altogether minus how much the original loan was. That means the Perez family will have paid $254,820.14 in interest. So they have paid over half of their original amount back in interest, which is kind of a crazy amount if you think about it. You try. Find the monthly payment and the total amount of interest using the information from the previous example, except our mortgage this time is only for 15 years and we have a slightly higher interest rate of 7%. When you've finished, go ahead and play the video and we'll go through this problem together. So we're still borrowing $220,000. This time our interest rate is 7%, so 0.07. We're still making monthly payments, so divide by 12. All over 1 minus 1 plus 0.07 divided by 12 to the power of monthly payments. Instead of 30 years, we now have knocked it down to 15 years. So $220,000. 0.07 divided by 12 is 0.00583 over 1 minus, well, since we already know that 0.07 divided by 12 is 0.00583, if we add 1 to that, we'll have 1.00583. And negative 12 times 15, we're making a total of 180 payments. Remember, that's to the negative power. So if we multiply the numerator, we'll end up with 1,282.60 divided by 1 minus 1.00583 to the negative 180th power is 0.35126. If we subtract we end up with 0.648784. And of course, when we divide, we'll end up with a payment of $1,976.93, which is, only about $600 more for a payment. If you could afford it, I would definitely recommend doing a smaller loan, obviously. But let's see how much interest the bank is making, knowing that we have $1,976.93 by 180 payments. That means the total we're paying back for this loan is $355,847.25. Subtract how much we only borrowed, which was $220,000. And when we subtract, the bank is making $135,847.25 on this loan for interest. So quite a considerably less amount of interest the bank is making in comparison to the last example. Casey borrows $1,000 for 1 year at 12% annual interest compounded monthly. We're not going to verify. We're going to say that her payment is $88.8488, or rounded $88.885. After making 3 payments, she decides she can pay off the remaining balance all at once. How much must she pay? So we can think of this as an annuity to find the amount presently due. So going back to our annuity formula, so currently, and we're going to use the most accurate, so we're going to use this payment here to keep this as accurate as possible. So one minus 1 plus, her interest rate is 0.12. We're making 12 payments a year, so monthly payments, to the negative 12 monthly payments, but we only have 3/4 of the loan left to pay because we've already been paying some of the loan. And since she already paid 3 months, she's already paid for 1/4 of her time since we're only in 1 year. So she has 3/4 left, or 8 months left to go. So 8 months out of 12 months is the same as 3/4. I'm sorry, she's got 9 months left to pay. 9 plus 3 is 12. So 9/12 of the loan left is equivalent to 3/4 of the loan left. Divided by 0.12 divided by 12. So 88.8488 times 1 minus, well, 0.12 divided by 12 is 0.01, so 1.01. Negative 12 times 3 is negative 36 divided by 4, so negative 9, all over 0.01. So using my calculator, if I were to take 1.01 to the negative 9th power and then take 1 minus that amount, I would end up with 0.08566 divided by 0.01. So what I'd like you to do using your calculator to verify is take our top decimal divided by our bottom decimal and then multiply that by 88.8488. And you'll see that her remaining balance to pay is $761.08 for her remaining balance. So an amortization schedule lists how much of each payment is interest and how much goes to reduce the balance, as well as how much is owed after each payment. So if you ever get a home loan or you have a car loan, you may end up getting one of these schedules, so you can kind of keep track of how much of your payment is actually going to principal, how much you're paying in interest, etc. So it's a good table to keep around so you can kind of get an idea of where you're at in your loan. So we're going to use the same information from the previous example, that Casey borrowed $1,000 for 1 year at 12% annual interest compounded monthly. Her monthly payment was determined to be $88.85. You'll see that in the in this category. I only have 5 payments here, but clearly this table could keep going until her principal is at 0. So we're starting at $1,000. We want to fill in this table, so we need to find out how much is going to the interest of her payment and how much is actually going to principal to pay down her principal. So we're going to construct an amortization schedule for the loan and determine the exact amount Casey owes after 5 payments. And you're going to be able to use this table for problems 22 and 24 in your homework, since they're directly related to Casey here. So we know that her interest rate is 0.12, and if we divide that by 12 months, her monthly interest rate is 0.01 monthly interest. So if I were to take my starting balance of $1,000 and multiply that by 0.01, our first payment, $10, would be going to interest. Well, if $10 is going to interest and my payment is $88.85, if I subtract the $10 from there, that means that $78.85 is going to principal. Well, then to figure out how much is left at the end of that payment, we simply take $1,000 and subtract $78.85, and we'll see that she now only owes $921.15. Let's keep going. So I have $921.15. Multiply that by my monthly interest. This time I'm only paying $9.21 in interest this period. Well, if now my payment is still $88.85 and I paid $9.21 in interest, My part that goes to principal is $79.64, so slightly more than last month. So now to get the principal at the end of this payment, we'll take $921.15 and subtract $79.64, and we will get $841.51. And we can continue. So I have $841.51 times my interest. That will give me $8.42 in interest. Notice how my interest is decreasing, while at the same time my principal payment is increasing. This should happen with all amortization schedules. Subtracting my interest, the portion that goes to the principal this time is $80.43. So again, taking $841.51, subtracting the $80.43, we'll get $761.08, which is exactly the amount that we had suggested after 3 payments, how much left she would have to pay of her loan to finish paying it off. So now let's take $761.08 multiplying by 0.01. And our interest that we pay is $761. So 88.85 minus 761, 81.24. Again, increasing. So 761.08 minus 81.24 gives me 679.84. And one final one, we have to take 679.84 and multiply it by 0.01 for our interest to be $6.80. And if we take 88.85 and subtract 680, we end up with 82.05. And then finally 679.84 minus our principal payment gives us 579.79. And you could continue this table until you reach a principal of 0. So you can kind of keep track that our interest decreases at the same time that our principal payment increases. So the amount that actually goes to the principal increases. And this concludes section 5.3, present value of annuity amortization.